Hello, everybody. Welcome on behalf of the Lumen Christi Institute. It's my pleasure to welcome Karin Öberg, and I apologize for mispronouncing her name, but I'm not going to embarrass her and me by trying to pronounce it correctly. Anyway, she studies the connection between planet formation, astrochemistry, and the origins of life. Asks such questions as how do chemistry and physics interact during star and planet formation, and how do they give rise to the organic composition of the nascent planets? How is organic material distributed in planet-forming disks around young stars? Questions like that. She has an experimental laboratory that simulates the chemistry and physics of interstellar grain mantles. Maybe she'll tell us what those are, I have no idea. Radio and infrared observations, often at high spatial resolution, and astrochemical theory. She left Sweden in 2001 for Caltech, received a bachelor's degree in chemistry in 2005, received a PhD in astronomy in 2009, with a thesis on laboratory astrochemistry. She then moved to the Harvard-Smithsonian Center for Astrophysics in October 2009 through 2012 with a Hubble, very prestigious Hubble Fellowship, where she studied protoplanetary disks. Went for a year to the University of Virginia Chemistry Department and then back to Harvard, where she ascended through the ranks. In 2016, she was named the Thomas D. Cabot Associate Professor in Astronomy, and then more recently she has become a full professor at the same institution. Her research in astrochemistry has been recognized with a Sloan Fellowship, a Packard Fellowship, a Newton-Lacey Pierce Award, among numerous other awards. If I named all of them, there would be no time for her talk. She is in great demand as a speaker in scientific circles as well as non-scientific circles. She's a very busy researcher and research mentor, and we're delighted to have her today. Here's the title of her talk. Please join me in welcoming her here today.
Thank you, Steve, for that lovely introduction, and thank you to Lumen Christi for having me. It's a delight to be here. I was at the astronomy departments and at the Department for Geophysical Sciences the past couple of days, and was very happy that I can add on this day so I can talk here with you. So in some sense, I'll be talking about the same things that I covered in the scientific settings today, but enveloped with some of my thoughts when it comes to why, as Christians or Catholics, for most of us, why we should think about these topics of exoplanets and potentially habitable and even inhabited exoplanets. I will probably talk for a little bit less than an hour or so there should be plenty of time for questions at the end. I'm very happy to take lots of questions. If you do have any sort of clarifying questions during the talk, please raise your hand. There's no point in sitting through the entire talk and sort of missing something on slide 2. Hopefully slide 1 is clear. And I will get to some of the concepts that Steve talked about, though perhaps not every single one of them, but you should also feel free in the Q&A. If you also want to know what these icy interstellar grain mantles are, you might have to ask at the end instead of hearing about it in the talk. So before getting to this topic, I do briefly want to advertise for those of you who are scientists and Catholics that there is a society for us, for you, that's a little bit more than a year and a half old now. That's the Society of Catholic Scientists. You can Google it and you will get to it, but also the web address is here. And this one is really meant for sort of 3 different reasons we started this society. One is just for fellowship among the Catholic scientists who I think often can be a bit isolated in their own departments, especially if their departments are small. But the other 2, and that's more the ones that I'm burning for, are to provide sort of a public an image for the public that science and faith are compatible, that there's no necessary conflict or even tension between the two. And the final one is to help out students who are, a bit more junior. I know that at least at Harvard there is some anxiety among the Christian students of how they're going to live out their faith as scientists. So feel free to check that out, and if you have any questions, I'm also happy to answer questions about that. Now, there is a myth that there is a conflict between science and religion. And I think it is a myth. I have yet to see any compelling arguments why there should be or historically have been a true conflict between science and religion. You can, of course, find some conflicts between specific people of faith and without faith, though most of the time it seems to have been between two different people of faith that interpreted Christianity or scientific evidence differently. If we're thinking about what we mean with that kind of conflict, I think you can think about it either as perhaps an institutional potential conflict, a philosophical one, or a psychological one. We can touch upon all of them, but I think the one that's clearly cannot be true is a psychological one. That is, that somehow being a person of faith would make you less of a scientist, or a scientist that would naturally lead you away from the faith. I think we have enough evidence of people who manage to combine the two that just clearly can't be the case. And here I've just pulled up some of the more famous Catholic scientists. I could also have put Galileo there, of course. If I had also, I wanted to keep it to 4 because otherwise it got too cluttered, but it would have been very easy to also find numerous Protestant great scientists who were very devout also for their age. And someone like Newton comes to mind, who wrote more on metaphysical and theological matters than he did on physics. So I think that is just clear empirical scientific evidence that this cannot be the real story, or at least the whole story, when it comes to relationship between science and religion. So the second thing I said is whether there should be, in some philosophical sense, a conflict between science and religion. Here, at least as Christians, I think it's clear that we are taught, and I think for good reason, that there's only one truth. And therefore, truth pursued through different means, if pursued honestly and accurately, cannot be in conflict with one another. And this is a very fundamental, in some sense, assumption, which within Christianity is backed up by a belief in God, who is the source of all truth. But it is something that I think also, when you're talking to people who are not necessarily people of faith themselves, something that is intuitively true. That it just would make no sense if you approached the same question from two different directions and you followed all the evidence, and the evidence were real, that you would get two different answers. And that is a very fundamental assumption that we make both in everyday life and when we do science or any other kind of intellectual endeavor. So I think as Christians, it should never be fearful to do science or critically pursue a question also with scientific means. It will eventually, like studying the stars, will eventually lead us to Bethlehem. So that is why I like this image. But moving away from that general introduction, I want this talk is going to be about planets around other stars and any potential, like what we know scientifically about them, the likelihood of there being life elsewhere, and then why we would want to study it and think about it as Christians or people of faith. Now, I think there's multiple reasons, or like multiple overlap between scientific and theological questions when it comes to this topic. The first one is just considering God as the creator, and that he reveals himself through his creation. So an accurate understanding of creation is good if we want to get to know our creator better. And this is, of course, true whatever topic you study. I mean, getting closer to the truth about the word is a good thing. But I think there is something special when we are talking about exoplanets and the appearance of exoplanets as a reality. I think that has, in a very real way, changed our cosmology, changed the cosmos that we inhabit. And when you're doing theology, thinking about creation in different ways, that is going to be implicitly or explicitly affected by the assumptions you make about the world we inhabit, or the cosmos we inhabit. So the first thing I want to think about then is God as a creator. Like, how does this discovery of exoplanets affect that? Well, to do that, I think it's good to just take a small detour into history and think about how much our understanding of the cosmos has evolved and how that might have affected how we think about God as a creator. If we look at biblical cosmology, it looks something like this. So what we have is, the pillars of the earth, the in-between, the underworld underneath, the in-between area where humanity lives, and then the vault that's separating us from the heavens. Now, this is there's something very intimate about this creation, which seems, at least at the first glance, to put humanity at the center of things. We are in this sort of central in-between region. The garden was created in this in-between region for us. There's a sense in which this whole part here was created for us. But if you look a bit closer at something like Genesis, I think it's actually quite clear that humans are not exactly central to that story. The main actor is God. And this is not the main place or the place where you finally want to end up. So I think one of the arguments that has been made as we are expanding the cosmos is it's making this story of God as a creator and his special relationship with man less and less relevant. I think you have to read the cosmology of the Bible in a very strange way to make that argument, but we'll come back to that. So the big development that happened in our understanding of the cosmos came with the Greeks, Middle Antiquity, late Greek Antiquity, when we are developing a more and more sophisticated version of what's shown here. So this is a cosmology where the Earth is sitting at the center, but it's a spherical Earth. That's something that was quite early understood, at least by the civilizations that lived close to the sea. And then you have the different planets, which people have realized that there are some of the stars that wander across the sky, and then they were put in orbits around the Earth. And then you have the fixed stars quite far away. And in medieval times, adopting this Greek model, they put basically the heavens on the other side. The heavens were that God inhabits on the other side of these fixed stars. Now, this cosmos is also is telling a slightly different story about God the Creator. We here have something that is wonderfully hierarchically ordered. There's a great sense, I think, of order and purpose in this cosmos. And also a clear separation of what's going on here on Earth and in the heavens. So here on Earth, things are corruptible. Where the planets and stars are, we have an eternal cosmos that is made of a different kind of matter than we have here on Earth. And again, I would say one of the criticisms against this and against the medievals, more rarely against the Greeks, is that it puts humanity at the center. But I think it's important to remember that this cosmology, going back to Aristotle and others, the center is not the place of honor. This might be the geometric center of the cosmos, but it is not the best place in the cosmos. The center is where things are heavy and gross and decaying and dying, while the beauty and the eternal things are out here in the heavens. And it was actually a concern among some theologians when people wanted to move to a heliocentric system for some good or not so good reasons, dependent on whom you read, that it elevated humanity and might lead to a more prideful mindset among humanity. So what happened then with Copernicus, Galileo, and later Newton is that we put the Earth among the planets. So either we raised up the Earth into the heavens, or I think more accurately, in some sense, brought the heavens down to Earth. It turned out that the same matter and principles that governs what's going on here on Earth also governs what the planets are doing. The development of these principles or natural laws in the 17th and 18th century was so successful that it started feeling sensible to think about the cosmos as a very, very good watch. Watchmaker is something that a watchmaker god or a mechanical universe are descriptions that seem sensible when you think about Enlightenment cosmology. So this is a cosmology where once you start something, once you put an object in motion, you can predict exactly what it's going to be doing for eternity. Where the laws of physics are perfect and they work on everything, and it makes for a very predictable universe. And you can maybe see how there's a temptation there to put the creator God at a large distance. Someone who gets it started, but if it's so predictable and just continues running the same way over and over again, why would he stay involved? And I mean, this is when we have the real development of deism historically. So this is, I would say, this kind of thinking about the universe, this mechanistic thinking, is one that many of us still have as our intuition. This is the physics we learn in middle school and high school, is still the physics of Newton. And I think it's easy to get stuck in this conception of the universe as something actually quite, not static in the sense that doesn't move, but something that doesn't change very much in time, and therefore doesn't need much intervention of any sort. But of course, we know that this is not the final word, and maybe this is not the final word either. But in the 20th century, a quite different cosmology developed, a quite different understanding of the origin of the universe. And that's the Big Bang theory. You know, one of the scientists that was on that first slide, Lumen, a Belgian priest who came up with a theory. And then this became eventually the conventional wisdom of how the universe formed, combining Einstein's equations, Lemaitr's idea, and Hubble's observations that we live in an expanding universe. So what is the Big Bang cosmology that we think that we inhabit? Well, it's something that changes over time, that unfolds over time, where new structures develop over time. It's a cosmos that has been around for a very long time on human timescales, for 14 billion years, which by some has been used to suggest that there's an awful waste of time if it was made for us to live in, who has been around for not very long. It is a cosmology. It's a cosmos that is incredibly large, which again has been used to suggest that we can't possibly be that important because there's so much else out there that's bigger than us, which seems like a terribly bad argument. I mean, elephants are bigger than us, and I don't think they were used to suggest that we are not important in the past. But I think maybe the most interesting part of it is that it's something that's actively unfolding over time. I think it's much easier to see how this would be an interesting universe for God to stay involved with also before there were humans like us to make it even more interesting for him. Now, this idea of a cosmology that's emerging is part of a bigger picture. I mean, if we look in biology, we have something similar happening about half a century before, or like almost a century before the idea of the Big Bang, which is the theory of evolution. So again, we have a nature that is emerging and evolving with time. If we look closer to home, and where I will be spending most of my time, so on stars and planets, we're also learning that they are not eternal. They are something that form and they are destroyed. And you form different things. You form different stars 14 billion years ago compared to what you do today. And you probably form different planets as well, and different planets around different kinds of stars. So it's understand. So what is exoplanets doing to change our cosmology again? Well, we still believe that the Big Bang cosmology is real, so we're not going to change that part. But I would argue that a cosmos is quite different, where when you look up on the sky, you see the stars, you look at stars in the galaxy, and each of them is somehow just a light, or if it is its own word, a star that's surrounded by planets potentially habitable. I think in some sense it makes the universe a bit of a cozier place when you look up on the dark sky, and you imagine that around every star there's actually a solar system with potentially people looking back to you. We'll get back to that towards the end of the talk. But before going into sort of more metaphysics and theology, I want to spend the next sort of 20 minutes or so just telling you where we stand on exoplanets scientifically. So exoplanets are detected in a number of ways, but the main reason, the main technique that's been used to find the most exoplanets is luckily also the most conceptually simple one. So I'm going to start with explaining that one. So if we're looking at the star, all stars are fairly distant, so we're not going to see the star result like we're doing here, like we would see the sun. But when we look at the star, and a planet passes in front of that star, you will see a slight dimming. And this is something that we can detect.
How many photons is that roughly, so it would be detected?
I have no idea.
You don't have any idea.
I have no idea. I mean, it's easy enough to look up, but in the optical, which is where most of these detections are done, people don't think in photons, and I therefore do not have it on the tip of my tongue. But we can definitely look it up together afterwards. So what is shown here is a cartoon of the kind of light curve that people look at to find exoplanets. So on the x-axis here is time. On the y-axis is brightness of the star. And then as you see, you'll see a dip in the brightness as the planet passes in front. Now, in addition to finding exoplanets, you can also say something immediately about the exoplanet by looking at just this light curve. You can imagine intuitively the bigger the planet, the bigger the dip. So we're going to be able to tell the size of the planet based on these kind of light curves. Also, the longer of it, the length of the duration here across of this dip in the light curve is going to tell us something about the orbit of the planet. You can imagine the slower the planet is, the longer it's going to take it to cross the star. So we will learn basically how slow it's moving, and therefore how far from the star the planet is sitting. So using this technique and others, we have ended up in a world where there are thousands of planets detected around other stars. So what's shown here is the number of exoplanets detected each year, going back to the first detection in 1995. And what I want you to notice is the y-axis, that we are now up in detecting like 1,000 planets in a year. There's some different colors. They're not super important. And this is also actually a bit dated from almost a year and a half ago. But what it does show here is that there's a single mission, this light blue and orange, which has provided most of these detections. There's a space telescope Kepler, which worked in exactly this way as I just described. Now, the fact that we have detected thousands of planets, what does that say about how often we have planets around stars? There is about 100 billion stars in the galaxy, and we have detected thousands. That does not sound that impressive after all. But we actually didn't stare at the whole galaxy to find these stars. We stared at a very small patch of the galaxy. And we did that in a way that you would only detect a small percentage of the planets, even for the stars that we were looking at. So the fact that we're seeing these many thousands of planets, that means that almost every star must have at least one planet around it. So when you look up at the sky, the stars that you look at will likely be worlds of their own. These planets don't look all the same. They come in a wide variety and shapes. We can't take pictures of these planets like we can of the planets in the solar system. So these are all artist impressions, but they capture at least the sizes that we see. And this is a small portion of the ones that have been detected. And that they come also in different compositions. We know that some must be gaseous and some must be rocky. So within the solar system, we have some planets that are small and rocky like Earth. We have planets like Jupiter and Saturn, that's mostly gas. And we see a similar diversity when it comes to the exoplanets, with some extra kind of weird planets thrown in for good measure that we have not seen here in the solar system. So going from the artist impression, what do these planets, what are they? What do they look like? So it shows a distribution of sizes of exoplanets as they have been detected by this space mission Kepler. And one thing to notice is that the most common planet here is this sort of weird in-between planet that's bigger than Earth, but smaller than Neptune. That would be the smallest planet of the giant planets in the solar system. That's the kind of planet we don't have in the solar system. So it's already telling us that we are not the typical planetary system in the galaxy. How atypical is still being argued, but what we can say for sure is that we're not the typical one, which is something to keep in mind once we get to the origins of life and possibility of aliens, a part of the talk. So where do we stand? Like what then does this teach us already? Does this teach us something about God as the creator? Well, it seems like the kind of planetary system we inhabit, while it's not special in the sense that it exists, there are planets around other stars. This has been sometimes used as an argument for challenging the specialness of us, of the creation that we inhabit, of our relationship with God. That seems like a strange argument for me to make. We don't know if they are inhabited. Maybe they're all there just for our viewing pleasure and excitement. I mean, that is still very much a possibility. We'll come to the likelihood of that in some time. But the fact that the creation or the cosmos is more interesting and more complex than we knew a couple of decades ago, I think is something that speaks to the extravagance and creative power of God, not much about his relationship to the inhabitants of Earth. So we'll put that to the side for a moment and just ponder that he has created a very interesting, very structurally rich universe that is constantly emerging. And that is something that's different compared to what people could imagine, I think, even 100 years ago, even though there were speculations going back into medieval times about that maybe stars were other worlds after all. And there's a couple of books on that, which I'm happy to recommend if somebody is interested. But we don't want to stay here. We want to understand what kind of planets these are, especially if we want to think about whether they could sustain life as we understand it or not. So how do we find out something more about these planets than just their sizes? Well, one of the things that we can do is weigh them, is to determine their mass. And if we know their mass and their size, we can say something of what they are made of. So there's a second technique to find and to characterize exoplanets, which is called radial velocity technique. So what we're looking at here is that normally when we think about planets orbiting the sun in our solar system, we think about the sun sitting still at the center and then the planets moving around it. But that is actually not true. If we think about what's happening, things about Newton's equations, what must be happening and what is in fact happening is that both the sun and the planets are moving at the same time around as the center of gravity, which is roughly at the surface of the sun. So it's very close to the center of the sun, but not exactly at the center of the sun. Now, more massive planets move the center of gravity further outside of the star. So in our solar system, the reason that we have the center of mass roughly at the surface of the sun is all due to Jupiter, which is a very massive planet. So if the star is moving, we can detect that by seeing the shifting of spectral lines from the star. As I said, I'm happy to talk more about spectroscopy at the Q&A if you're interested, but for now, sometimes just take my word for it that there are spectral lines that emerge from stars, and when the star moves, those lines move as well, and we can detect that wobble of those lines, and with that we can weigh the planets. When we then make a figure where we show the mass of the planet versus the size of the planet, we can draw some conclusions of what they're made of. So that's exactly what's shown here. Masses of some detected exoplanets, radius of the same detected exoplanets, and then these different lines here shows the expected relation between radius and mass for different compositions. So if the planets are made all out of iron, that's pretty much the most dense planet we can think of is that it's just entirely made out of iron. Then you should have, for a mass, let's say 10 Earth radii, you can get to that mass with a pretty small radius. But you could also have planets that are made out of gas. In that case, you're not going to get to a mass of 10 Earth masses unless you have a pretty big planet. And what we find, which I think is one of the exciting results coming out of the recent exoplanetary studies, is that when we're looking at small planets, so planets that are of the order of this roughly the same size as the Earth, so this is all in Earth radii here, at least most of them tend to fall on this line that corresponds to rock, and that's where the Earth would fall as well. So small planets have a tendency to be rocky. Now, why is that exciting, you might ask? Well, we think that the chemistry here on Earth that eventually led to the origins of life, though, as we'll come to, it's very unclear what this chemistry was and how much of it we understand, but that having a rocky sort of substrate to work on was important. That it's not going to be easy to have an origins of life if you have a gaseous planet, for example. There's no chemistry that people have thought of that would make that happen. Now, what's even more exciting is that a subset of these small planets, they have been classified as so-called habitable planets. And with subset, I mean, we're now talking about between 10 and 15 of them, maybe 20 for those who want to be more generous. So these are detected exoplanets around other stars that astronomers have deemed to be habitable. Now, it's important to understand what habitable means when we're thinking like astronomers. It means something very minimalistic. All it means is that the planet is sitting at a distance from its star where water could be liquid. That is it. There's a rocky planet, and on the surface, there are at least some atmospheric conditions under which water could be liquid. Now, this is obviously not all you need for life to, well, we don't know how it originates, but if you have life, you can't sustain life with just the same temperature. So we'll talk some more about the other ingredients soon, but that is already an exciting discovery. What's even more exciting is that the number of planets that fall into this category is likely much, much larger than these 12 or 15, which are the ones discovered so far. There have been different statistical analyses thinking about how often you would expect to have one of these planets around the star. Different scientists come up with slightly different numbers. This is still a field that's very, very active. But most come up with numbers that are something like between 5 and 50% of the stars in the Milky Way have a planet in the habitable zone. Most of these stars are not stars like our own. but they are rather tiny stars. We call them M dwarfs. They're red, small red stars. They're the most common star in the Milky Way. And these are the ones which seem, from the current data, to very often possess a planet in the habitable zone. One of the most famous systems, which made the news, I guess about a year, 2 years, is it a year or 2 years ago? Not that long ago. So thank you, Dan. About a year ago, is the TRAPPIST-1 system, which is actually a fairly nearby system. So this is a small red star that has 7 planets around it. And several of these planets are in this so-called habitable zone. So these planets are not rare. And actually the nearest star, it's just Proxima, seems to also have a star, or like have a planet in its habitable zone. So this is exciting. I mean, these are things that are not that far away. We're talking about light years or tens of light years for these different systems. Now, one thing to just keep in mind when we're talking about these systems where you have a red dwarf star is that the habitable zone will be quite different compared to the habitable zone that we are sitting in around our star. These, as I said, are tiny stars, which means that you have to get very close to the star to be warm enough to have water be liquid. So this shows a comparison of the TRAPPIST system and the solar system with a habitable zone marked in green. So we are obviously in the habitable zones, and Mars is as well, which should be actually a word of caution because Mars does not seem very habitable today. And also Venus is right on the edge of the habitable zone in most people's estimations, also not very habitable. But what I really wanted to show is the whole of TRAPPIST system fits well within the orbit of Mercury, so very, very close to the star. And that might lead to actually to quite different conditions on the surface of these planets compared to what we are used to. Sitting that close to the star makes you a bit vulnerable to any stellar activity that you have going on. So that's something that people are looking into, and that I will happily ignore for the rest of this talk. Okay, so we have these planets that are potentially habitable in that they are the right temperature. Now, as I said, that this right temperature is set by one sole criterion, that you could possibly have liquid water on the surface. Now, what is the likelihood that these TRAPPIST planets, this is an artist impression, we obviously have not been to TRAPPIST and taken pictures. You can see the other sister planets in the background. So what is the likelihood that one of these habitable zone planets actually look like this instead of being like an arid desert? And why is it so important anyway? Why should we use water as our criterion for habitability? Well, starting with the second question, water is obviously very important for life here on Earth. But that is not the sole or even the most important reason that people focus on it when it comes to exoplanets. At least not officially. I mean, we all, of course, go in with biases. But the official reason why we're so interested in water on other planets is that water really allows us to have the most diverse kind of chemistry when we're thinking about different kinds of solvents that you could have chemistry happening in. So, and to have biology, you need to have chemistry. You need to have an efficient and diverse, we think, organic chemistry. And so it's an excellent solvent, and it also happens to be a very common molecule in space, as we'll get to, which is a good thing when we're thinking about what would we expect other sort of living environments on other planets to look like. But before going there, let's think a bit about our solar system. How special are we in the amount of water we have? And how special is the Earth in the amount of water it has? Well, within the solar system, the Earth is not that special at all. So what's shown here with the blue balls next to the planets or moons is just the volume of water that you have in each of these bodies in the solar system. So here's Earth. We actually don't have that much water if you think about the whole size and mass of the Earth. Here are some of the moons in the outer solar system. Europa, Pluto, not the moon, but former planet. If anyone has questions about why, I'm happy to elaborate. Triton, Callisto, Titan, and Ganymede. So all moons in the outer system. And my favorite one, which we'll come back to, which is Enceladus. So in the solar system, water is fairly common. It seems like the entire solar system formed in a water-rich environment, and that the Earth just got some water thanks to being in this overall water-rich environment, formation environment. So a very fair thing to ask then is, how often do planets form in water-rich environments? Well, to answer that, we're going to have to just spend a few minutes thinking about how stars and planets form. So this is going to be your sort of introduction to star and planet formation. So hang in there, and I think it's not going to be too complicated, actually. So between stars, space is not empty. If you look at the regions between stars, there's dust and gas. Now, there's not that much per like, cubic centimeter or per cubic meter, but it's there. And there are some regions between stars where this dust and gas gets concentrated into what we call interstellar clouds. If these interstellar clouds get dense and massive enough, they will start to collapse in on themselves from their own gravity. And that is the beginning of star formation. So as one of these clouds collapses to form what we call a protostar, it's just a star in the making. In addition to the central star, which will be where most of this collapsing mass go, you will also see a disk. This disk is there because the initial cloud always spins a little bit. And it's one of the laws of nature that you have to preserve the spin of something, or angular momentum. And to preserve that, you put most of the mass in the central star, and then most of the spin or angular momentum into the disk around it. This disk, this leftover material, is where planets form around stars. So what we're really asking is, how often, when planets are forming in these disks, are these disks full of water? I mean, that is the question that we're asking. Now, we can't study the water content of these disks directly. We just don't have the technical capability to do it. If you want to spend about $5 billion of your taxpayers' money to build another space telescope, it will be trivial, but we don't have that. So we're blind to what's going on here in terms of water. We can't see what's going on over here, though. Here we can use spectroscopy. So that's just how matter interacts with light in a very specific way that allows us to tell what kind of molecules or matter you have when you look towards a certain star. So when we look towards these protostars, and we look in the infrared, we see spectral features that we can associate with water. In fact, water is the most abundant molecule that we see next to molecular hydrogen and carbon monoxide. So it's incredibly abundant at this early phase of star formation. As I said, we can't see what's going on here, but in the solar system, we do have a leftover of our disk, which is comets. Comets is something that visits the icy bodies, that visits the inner solar system, and we can take spectra also of them and figure out what's going on there. So the idea is, and the argument I'm going to make, is that by looking at comets, we can show that our disk actually inherited its water from up here. And if our disk inherited its water from these early stages, then other disks probably did as well, and therefore water will be generally available to planets. Now, the way we do that is also with spectroscopy. And I promise this is the last slide on spectroscopy, well, second to last one. But what we can tell when we look at comets is that we can distinguish, first of all, comets have a lot of water, but we can distinguish whether that water is normal or whether it's heavy. So you've heard of heavy water. Water is normally 2 H atoms and 1 oxygen atom. To make heavy water, you replace one of those hydrogen atoms with a deuterium atom or a heavy hydrogen atom. Now, getting the ratio of the heavy water to the normal water allows us to say where the water came from, because that's very specific to where it formed. And the ratios we see in these comets can only come from this protostellar water. So we really did, the water in the solar system is really older than the sun itself. And that to us makes it for us very compelling evidence for that planets in general form in water-rich environments. So we think we are good on that first criterion, that if planets are temperate to the right temperature for water, they probably do have some water on them. Not all, but probably most of them do. But there's a second ingredient that we need to think about, and that is the organic material. So if we want to have an interesting chemistry happening that leads to life, we need to have some organics that actually react in the water that we now think we have. But the whole point of having water was there was a good solvent for chemical reactions. So how often do we get what we think we had here on Earth at the early stages, which is that water and land, and then lots of organic molecules swimming around in those ponds or in those lakes that we had on the young Earth. Well, before getting to that, I think it's good to think a little bit about what we know about, like, which of these molecules are going to matter. To do that, we need to think about the origin and evolution of life here on Earth, at least what we know about it. So we know that life has developed on the Earth over many billions of years. The exact starting, when the first life showed up, is contested. But once it showed up, we had a long time of development of more and more complex single-cell organisms. And then eventually, about half a billion years ago, 2 billion years ago, we started developing larger multicellular creatures and eventually mammals such as ourselves. Now, the origins of life, we can put some boundaries on it that I think everyone would agree with. One is that we don't think it's older than the Earth itself, or when the Earth first cooled down to become possible to have normal chemistry, which was a few 100 million years after we had this big impact that caused the moon to form. Around 3 billion years ago, there is compelling evidence for water when it comes to different kinds of fossils. However, there is evidence that suggests that that's 3.5 billion years ago. So this is just maybe 500 billion years ago after it becomes possible to have life on Earth. There's already life from sort of fossils of bacterial colonies and potentially some isotopic evidence that is more contested. But I think what the real point I want to make is that it didn't take that long for life to develop here on Earth once it could develop. And it actually took much longer for life to leave the single cell stage behind. Now, how do you get, though, to this very first living organism, which there are debates whether it's definable or even something you would want to define, but something that could, where you could have inheritance from species to species as well as some metabolism? Well, to that, you probably had something that looks like RNA was probably what the first species were composed of, maybe hundreds of units of RNA. So you want to know how that hundreds of units of RNA formed. To understand that, you need to understand how the building blocks of RNA form. And to understand that, you need to understand where the building blocks of the building blocks come from. And there's been many thoughts about that. The most famous one is maybe the Miller-Urey experiment, where they took what they thought was a good analog to the early atmosphere here on Earth, put a charge through it, and looked at all the interesting species they formed, including amino acids, and called victory because they had managed to almost create life out of inorganic material. This is no longer a favored scenario to get to the building blocks, but there are other scenarios that seem to work better. The most popular one right now is that you have hydrogen cyanide as a very important ingredient, and then lots of UV light. That seems to get to actually all the building blocks that you would want for then forming these biomolecules. So then you can ask the question, how often do we see molecules like this in disks where planets are currently forming? How common is it for planets to form in these environments rich in these key organics? That is something that we can actually start to address with current telescopes. So this is a cartoon of one of these disks around a star. There's an amazing new telescope down in Chile called ALMA, which allows us to study these disks in great detail. So with that, we can see great structures. These are some before and after picture, what we could do before ALMA came, what we can do now. So here are these two blobs, are actual observations of these disks, but as you can see, you can't see very much at all. With ALMA, we can see that these disks really look very much like the cartoons that we had before. So what you see here, you can also come up afterwards if the light is not good enough, is that we see these dark lanes carved out in these disks that we think are due to planet formation, one way or another. You can think about the planet forming as sort of carving out these lanes. We can also take pictures of the chemistry that's happening in these disks. And we also see similar kinds of structure that's telling us that we can make associations between the physics that's going on in these disks and what kind of chemistry that you will have available for planet formation. In particular, we can so this is the same disk that I showed before, so the same kind of structure. In these disks, we can use again spectroscopy, and this is actually the final time that I'm mentioning that word, to tell that you have molecules such as formaldehyde. One small, fairly common organic here on Earth seems to be very common also when you have planets forming around other stars. And this is not the only one molecule we are detecting. We're detecting lots of little hydrocarbons, cyanides, which not very good for you, but very good for the origins of life. As I said, this is like the centerpiece of current origins of life chemistry theory. And as you just saw, formaldehyde and methanol and other nice small organic molecules. So how often do planets, if a planet forms in here, how often does it actually manage to accrete these molecules onto its surface and into its atmosphere, where you could actually have an interesting origins of life chemistry? Well, we can do theoretical work on that, but to finally answer that, you really want to take spectra of these exoplanets, and I guess that was one more time, and actually check directly what's going on in these atmospheres, in these planets. And just an example, you see here that in theory, if you could take, do perfect observations of planets, as perfect as you can do here in the solar system, you should be able to tell the difference between planets that have, a nice water and ozone-rich atmosphere compared to planets that are probably dead, that have mainly CO2 in their atmospheres. If you really want to check whether these planets are not just have the right chemistry, but are actually have biology, you are probably eventually going to have to take a picture of them. This is going to be really, really hard, but not impossibly hard. I guess that's I want to give it a hope that this is not something we're going to do next year, probably not in 10 years, but on sort of a civilizational timescale, this should absolutely be possible. So what's shown here is, to get a certain resolution, how big of a telescope you would need to see an Earth at this resolution in the sort of some of the nearest planetary systems. So to see this, which is probably going to start telling you that there's an ocean and maybe vegetation going on this planet, you would need a telescope of roughly 460 kilometers big, which you're not going to build in a single dish that size, but you could build multiple dishes that talk to one another that size. going to be really hard. But as I said, not actually totally impossible. So where I want to end up is in thinking about what we know, what this tells us about our place in the universe. I think with a wealth of exoplanets, we've already seen this sort of wonderful creativity that's flowing through the universe. But I think there's also a bit of anxiety in many in thinking about, well, what if they're all inhabited? I mean, how special or non-special does that make us? Does that make sense in the story of creation as we understand it, with our what seems to be a very special friendship with God? So before getting to that, and I just wanted to sort of recap where we stand, so we actually know where we are. So we have planets around almost every star. Many of these planets could potentially sustain life. They fulfill the minimum criteria of what we think are needed for the origins of life. That is the right temperature, access to water, and access to many of the key organics that we think are needed. Now, minimum requirements does not mean that life will originate. We do not know how life originated here on Earth, whether it's a really easy natural process, whether it's a really, really difficult natural process that happens extremely rarely, or if it's a natural process at all, which, as a scientist, it's not going to be your starting hypothesis. I'm obviously trying to find the natural path to this. But that is not something that we at this moment know, because we don't know that pathway. And so we're going to have to hold both possibilities in our hands, both that maybe each of these planets has life, or that none of them do. Now, I said I think we are, on a civilizational timescale, we're going to figure out that we're going to get an answer to that question. And which it ends up with, I don't know, but I think we're learning something about the Creator, like once we do. Imagine that every one of these planets is filled with life. There's something exuberant and almost playful about that thought. And I'm not talking about intelligent or rational life at this point, but just life at all. Something about the extravagance I think it makes sense to many when you think about sort of creative power of God, that would be the kind of universe to expect. Now we know that many of the natural conditions are fulfilled. But there's also some beauty to the opposite. There's also something greatly extravagant about the God that created an entire universe just for us, and that we are sort of the lone ark carrying all of life through space and time in the universe. But I think you would get a different intuition about God as a creator and God's sometimes personality, if you can use that word, about God, dependent on which of those turn out to be true. Now, going to exoplanets and figuring that out, or studying exoplanets to the detail we need to figure this out, is going to take some time. But I would argue that you actually don't need to go all the way to exoplanets to start getting an idea of this, whether this is true or not. We do have places in the solar system that also fulfill many of these minimum requirements. Remember that initial slide I showed, where it showed there was water at many places in the solar system? We think that where there's liquid water, which there is in a subset of those bodies, there's also organics, and therefore potential these origins of life for origins of life chemistry. Particularly, there are a couple of moons in the outer solar system, Enceladus and Europa, which have this liquid water for sure. Enceladus is my favorite. Both of these moons have an icy shell and then a subterranean ocean of water. Enceladus is my favorite because it's spewing out some of its water into space, which means you could probably actually go there and figure out what's in that water without as much cost as it would take to actually drill down into one of these moons. So this is obviously something we should do. If you ever are in power, we should go to Enceladus and figure out what's there. But where I want to end up is just going back to the specialness of us, the creation of us, when we're thinking about exoplanets, and whether that in any way is threatened by the possibility not just that there's life elsewhere, which I think is most people find delightful and not the least threatening, to whether there is rational animals among those animals and vegetation and beings. There is, of course, biblical sources of extraterrestrials, as we all know. They have visited many times. They're called angels. But I would make the argument that, well, these, of course, do not in any way threaten the special friendship between God and humanity. But that these are maybe not that good of an analogs when we're thinking about aliens. These are, St. Thomas Aquinas, I think, would call them intellectual beings or spiritual beings, while we are rational animals. And there is clearly a different kind of interaction between them and God compared to between us and God. So how about other rational animals? Is that likely? Is it theologically possible for that to happen? If so, is it necessary that they fell? If it's necessary that they fell or possible that they fell, how would they be saved? Would they be saved through their own having their own incarnation? Or would they somehow be saved through the incarnation, as I think is the most straightforward reading of the Bible, that Jesus died once for all. But I think you could also argue that it could be all humans. Well, I don't know what is plausible, or even, or obviously not what has happened, since we don't even know if these rational animals exist. But I was delighted to find out that St. Thomas Aquinas sort of thought about this a very long time ago, the possibility of having incarnation happening more than once. So the first thing is that he discusses is, why was it possible or fitting for having incarnation at all when it comes, why was it fitting for God to become incarnate as a human being, rather than say like as an angel or some other animal? And St. Thomas identifies two criteria for this fittingness. One is the dignity of the being, and among the material beings, the humans clearly have the highest dignity, at least here on earth. The other is the need for salvation. There are some theologians that argue that incarnation could happen without there being the fall or sin. St. Thomas does not believe that. So he thinks that these two criteria are what is needed for the fittingness of the incarnation. So this could, of course, apply to other rational animals as well that should have a similar dignity. Furthermore, St. Thomas also thinks about, could you have the incarnation happening multiple times? Could other persons of the Trinity become incarnate? He says absolutely yes. There's no reason that this would not be within God's power. His power is not lessened by the first incarnation, or as I think is many of our intuition, the only incarnation. So philosophically possible, yes. But then, of course, it comes to the correct interpretation of some of those Bible passages that, as I said, at least the most straightforward reading seems to be that it only actually happened once. But with those Thomistic reflections, I would like to end this and open up the floor for any questions. I think you're absolutely right that is an interesting line of inquiry. I can't say that I've done much beyond reading C.S. Lewis' Space Theology, which is, is a fun one for those of you who are interested, where he actually thinks about exactly that. What would it be? He imagines, I think it's the Martians. They have not fallen. What is it like for them? How could they interact with these purely intellectual creatures, which we only seem to do with great difficulty, and they do not. But also about their sort of wistful looking towards Earth, where the incarnation happened. And there is, I think there's definitely room for reflection there by someone who has somewhat more theological training than I do. So thank you. I don't know. So will be purely sort of off the cuff. I think there's what I was getting at more was just a very basic intuition that it seems easier to fall into the temptation of deism if you set up a physical world there where things are not interesting, where they don't change, where they are extremely predictable. Of course, I mean, God is outside of time and he can see everything in a sense, and maybe for him things are not boring if they repeat over and over again. Chesterton has a wonderful passage where he considers why the sun rises over and over again, that maybe it's just because God is in some sense like a 3-year-old in that he delights so much in seeing this wonder of the sun rising again that he just says, do it again every morning, much as a child says for reading the favorite book. So I'm not sure that, I'm not sure there's any compelling metaphysical reasons why God would have less of a thing to do if you have sort of an eternal universe, and certainly you can still have a creation of an eternal universe. Only that it's easier to fall into the trap of thinking that God is not needed. While when you have the emerging universe where it's clear that they're not clear to have a creation ex nihilo as we think about it theologically, but you have what seems to be an image of it. So that makes it easier to have an intuition of a creator that is actively involved. So I think that was more what I was getting at rather than any good philosophical elements. Yeah, so there's a couple of questions that I totally ignore them for most of the talk. One is simply practical, that we can't detect them. Or like I shouldn't say we can't at all. There are attempts to detect them, but it's much harder to detect them than it is to see these planets around these red dwarfs, which is why we have many of these planets detected around red dwarfs, but necessarily not any moon yet. Though I said there are attempts to do it. So that's a practical reason. The other one is a more chemical or physical reason, which is that, well, for some people, the minimum requirements are met for these icy moons. The most popular scenario for forming these early biomolecules is interactions with UV light in ponds, rather than having oceans that have a protective layer on top of them. And at least that chemistry would not work on something like Enceladus or the other moons that I showed. So that lower the probability somewhat within the current framework. So that would be, but if we find life on one of the moons, absolutely that would up the number. I don't know that I have a good answer to that. I would say that there is a personal intuition of that. There is, also, let's say, the diversity and interestingness of his creative power. That it seems like where there is room for something interesting and creative to happen in the universe within sort of the natural laws, it happens, and that is. It is a more and more interesting universe that we inhabit. That to me makes sense in thinking about God. I think everything we learn also from Revelation would suggest a God that is extravagant in many ways. And that seems to ring very true with the discoveries we're making. But it's difficult, I think, to go much further than that because we know so little whether that interestingness actually extends to more living beings, which in some sense my intuition says they do, otherwise I would not be spending so much time on these research questions. But I have no scientific evidence really to think that beyond this a certain intuition. I think this is very common among scientists, whether they want to acknowledge it or not, that we pursue certain questions based on some sometimes very strange metaphysical ideas. I mean, if you talk to a particle physicist, and I don't know if there's any in the audience, they are overall absolutely convinced that there is one unified theory that will explain basically everything. I mean, if you look at the mess that is the world, there's no real reason to think that that would happen, beyond that they seem to have approached it in the past, and therefore, and beyond that there is some idea that there is a unity to the truth of the word that we should be able to uncover. And I think I have something similar here that based on my relationship with God, my understanding of the Bible, I would expect him to not just fill the universe with interesting planets, but also with interesting things on those planets. It's a combination. So it's easier, as you can imagine, it's easier to detect larger planets. They make a bigger dip when we are looking towards stars. So we are absolutely more incomplete in our detections of smaller planets than we are of bigger planets. So if we could observe the small planets as well as we could the bigger ones, there would be many more planets on the smaller scales. Especially when we go down to Mars-like planets, we can see almost none of the ones that we think exist. Still, there seems to be that the most common planet that's out there, that's even taking into account some of these biases, are rather these in-between planets. At least when we look at solar-type stars. When we get down to red dwarfs, might be a different picture, but when we look towards stars like our own, it seems like these slightly bigger planets are, if not the most common, at least very common, and we don't see those in the solar system. So something in between. Well, so if you have a very small planet, such as Mercury or even Mars, you have a very much higher likelihood of losing your atmosphere, which is bad for life. I mean, I'm not a biologist, but I don't see any reason that you can't develop cell-like life on a smaller body. So I think it's more a question about the atmosphere. And similarly, what we seem to see is that once you get to a certain planetary size, you stop having these rocky planets and start having more icy and gas-rich planets, which are not as impossible, but we don't really have any good theories for what kind of life would develop there. Again, I don't think it comes down to the cellular structure, the structure of life, as much as the chemistry leading to it. Yeah, so starting with your second question, if we see these dips and we observe the same star for a very long time, it is typically not trivial, and it gets harder the further out the planet is, and therefore the longer it takes to go around the planet. But you can distinguish the different dips. From the same planet, you will have basically the same depth of the dip every time and the same length, more or less, with some qualifications. And so you can distinguish between different planets, as they did here in the TRAPPIST system. So what was your first question?
Typically, how many planets would a star have around it?
We don't know. And the reason we don't know is that we are currently doing a pretty good job on detecting planets that are on orbits that's less than that of the Earth. And the reason for that is simply that you need to see the same planet. Well, it's easier to detect a planet if you can catch multiple orbits. And the mission of Kepler was designed to be able to catch something like the Earth a few times. But things that are further out, you're not going to catch more than one time. That makes it less likely that you catch it, and more difficult to be certain that you actually saw a planet if you do. And at least in the solar system, more than half of the solar system is further away than the Earth. So we do often see multiples, but as far as I know, we don't know what the characteristic number is yet. So I don't think I have special divine inspiration, and therefore that my hunch will count more than yours. I would think it would be so amazing to chat with some rational animals of a different kind and hear what their relationship to God is, and if God became incarnate, how was it? So it's a hope. It's not a hunch, and I don't, I guess, have that much hope it will happen in my lifetime. So yeah, sorry, boring answer. So people have definitely thought about different things. So I'm going to limit myself to chemistry-based life, because once you leave chemistry behind, it becomes quite far-fetched, I think. So the reason that carbon, there's a couple of different reasons that we primarily think about carbon. It is one of the most common elements in the universe, so there's a lot of it, which is a good thing. It can form 4 bonds with other elements, which makes it very versatile in chemistry. And it can form, and they form very many different structures. Now there are other elements that can also form 4 different bonds, but they tend to not they're rarer, and they don't form generally as stable of structures. So people have thought about that maybe when you are at the planets that are very cold, where you have hydrocarbons instead of water solvents, maybe you'll also get something else when it comes to the actual building blocks of life. But and it's not, it's not something I would rule out, but it seems like it's going to be rare compared to carbon-based life for these reasons. But yeah, there's definitely something people have pondered. Yeah, no, so it's a great question. So stars come at a range of masses and therefore luminosities and temperatures. So that all hang together. Lower mass, lower luminosity, lower temperature, which makes them look redder. Higher mass, higher luminosity, higher temperature, which makes them look bluer. And the sun is somewhere in the middle of that. Now, when we go to stars that are much more massive than the sun, so more than a factor of 2 more massive, we don't spend that much time thinking about them because they're relatively short-lived. And that means that you would have much less time for life to develop. So we go from having billions of years for life to develop to having hundreds of millions to tens of millions as we go up the size scale of stars. So we tend to not think about the more massive stars that much. When we go in the other ends, we go down, they become more longer-lived, which is a good thing. And that's what most of the stars in the galaxy are these smaller, redder stars. Now, one of the things that might limit the habitability around these smaller stars, I hinted at that, is that the planets have to be very close to the star. And that means that they get exposed to things like stellar winds, so analogs to solar winds, in a totally different way compared to how we're exposed to them. And at least many of these red dwarfs are quite X-ray active, so there might be some, and not as UV active. I mean, I said we needed this UV light for the current ordinance of life chemistry here on Earth. So that might be a limitation, that the different radiation fields that you get around these smaller stars compared to the sun, and we just don't know that, how limiting that's going to be. But there's people are thinking about it. Okay, so the Fermi paradox is if life originates, this easily, like you just need these minimum requirements, or even if it doesn't originate that easily, but at least once every hundreds of billions of times, that's not that often. And we think about how, so then there should be at least one other civilization in our galaxy, right? And then we think about how rapidly our technology has developed. That it's not totally far-fetched to think that if it continues in this rate and will go on for a few million years, which is a very short time scale when we're thinking about cosmology or stellar and planetary evolution, we should be able to move from star to star in some way. So that means that the likelihood that this other civilization has a few million years head start on us is very high when we consider that the galaxy has been around for about 10 billion years. So where are they? Like, why don't we see any aliens? I think that is an excellent question, and I think it's one that can be used arguing against that even if life originates quite easily, even if complex life originates quite easily, that there's no natural means to get from, that's what we believe, right? But this would be maybe some scientific evidence for that there is no natural process to move from just complex life that's purely matter to rational animals. That has the kind of technological development that seems to have come natural to humans. Now, there are some counter-arguments to that. It might not be that easy to move from star to star, even if you continue to develop technologically. Are people really going to want to move, like to spend a few generations on a starship to go to another planet that may or may not be able to colonize? It seems like it would have to be a very special civilization to do that. Something like the Polynesian civilization here on Earth, where they sort of did that. Though not for generations, but at least for many days or weeks. So it's not obvious to me that that's actually something that would happen just because you go on for millions or hundreds of millions or even billions of years. Even if you do, it might not be that it's that easy to detect very advanced life. That's been something else that's brought on. So I guess I don't find it super compelling, but I think it's something but it's also something that is difficult to get around. Why we don't see any evidence for it, I guess, is very non-committal. Well, what has been argued is that a very advanced civilization would not be limited by planetary energy. They would harvest the stellar energy much more directly, in which case this might not be as much of an issue. I guess would be still, would it be something people would do unless they were in pretty dire situation? I don't know. That doesn't seem like it's something that has to happen just because you go on and technically develop for many millions or hundreds of millions of years. I think that exploring the universe seems like a very compelling thing for me to do. I think that forcing people to go there colonizing seems like a bad, immoral thing to do. Letting people who want to take part of that sort of exploratory journey and giving them the resources, if we have if we can come up with a technology to do it, seems like something that, would be an obligation almost to do, to try to get to know this universe a bit better. Some of my argument was that by getting to know the universe and the creation better, you do see some new facets of the creator. In that sense, I guess also theologically the right thing to do. I am extraordinarily embarrassed to admit that I have not seen Interstellar, despite my connection with Caltech and where they got much of the physics from Kip Thorne. So no, I have no comments on it, I'm afraid. Somehow I haven't been watching movies for the past few years, which is, yeah, I had other things to do, sorry.